Another type of circuit we see inductors in is what we call an LC circuit, meaning we have an inductor and a capacitor. LC circuits are very common in anything with a tuner, so your radios, where you change radio stations that you want to listen to, it's an LC circuit in there. They generally, as you tune your radio, for example, you have either a variable inductor or a variable capacitor. And so the value of the capacitor or the inductor changes as you change the radio station, as you dial to a different frequency. So in an LC circuit, number one, something needs to bring energy into the system. So either the capacitor needs to have been attached to a battery and charged up, or the inductor needs to have been attached to the battery so current was flowing through it. Either way, one of them comes in with energy. So I'm going to go ahead and say, for simplicity's sake, that our capacitor is coming in charged. So it has some Q0, some initial charge, and a capacitance C. That capacitor is attached across an inductor. So the circuit we're looking at the moment, the battery, there's no battery anymore. No more battery connected to it. Well, what's going to happen? Just the first thing. What do you expect to happen?
Nothing. It's fully charged. You can't get a current.
But there's no battery to keep the charge there. There's nothing to force the charge to stay where it's at.
So current will start flowing from it.
It's going, the capacitor will start to discharge, so current will flow through the circuit. But the inductor, not too happy with it. The inductor's going to try to oppose the change in current. So the inductor slows the rate at which the capacitor can discharge. The capacitor can't just, boom, be done and discharged. The capacitor is going to slow the rate at which the capacitor can discharge. But the inductor is always happy with whatever situation it just had. So once current is flowing, it's perfectly fine with that. It just doesn't want the current to change. Well, at some point, the capacitor's charge is going to go to zero. The capacitor will become completely discharged. At that point in time, all of the charges are moving as current through the circuit. But if the capacitor is completely discharged, it has no more charges to feed to the system, so the current's going to have to go to zero. But the inductor doesn't want the current to go to zero. It was perfectly happy having current. So what will happen is the inductor will induce its own current and force the charges up until the capacitor becomes charged with the opposite polarity. So basically the inductor charges the capacitor again. But once the capacitor is completely charged, it discharges again. But this time, current will flow the other way. And current flows until the capacitor is completely discharged. But then the inductor induces current, which in turn charges the capacitor back the other way. And we go through this cycle over and over and over again. It's an oscillating circuit. Similar to like a mass on a spring. Pull the mass down, bounces on the spring. Without any resistance in the circuit, the total energy has to stay constant. Right here, when the capacitor is completely charged, the total energy is within the capacitor itself. So when the capacitor is completely charged and there's no current flowing through the circuit, the capacitor has all the energy, and we can figure out how much energy it has from knowing how much charge it has and its capacitance. When the capacitor is completely discharged, we have all current, a maximum value of current. The total energy is in the inductor. If we're anywhere in between those, between the capacitor being completely charged and the capacitor, and having current flowing, then both of them will have a portion of the energy. Q being however much charge the capacitor has that's not a maximum charge. I being how much current is flowing through the inductor, but not the maximum value. If the current is maximum, then the inductor has all of the energy. If the charge is maximum, then the capacitor has all the energy. If it's something in between, if you have some charge on the capacitor and some current flowing through the circuit, they share the energy. Not necessarily equally, but they do share the energy. So conservation of energy, perfectly applicable. Now, if you throw in some resistance, which realistically you have some resistance just for the fact you have wires, the resistor will take away some of this energy. And if we were to graph, right now the graph, if we graph charge versus time, without any resistance, it's a perfect sine or cosine wave. The amplitude never dies. With some resistance, that amplitude will die down and eventually go to zero. So, a couple of equations besides energy that are applicable in an LC circuit. Kirchhoff's loop rule. We know the voltage drop across the capacitor plus the voltage drop across the inductor. Sorry, that's not going to be. Those have to add to be zero. There's only two elements in the circuit, so their voltage drops have to be zero. That means whatever voltage drop the capacitor has is equal to the voltage drop the inductor has. Just opposite in polarity. Now we know the voltage drop across the capacitor is Q over C. And we know the voltage drop across the inductor is L di dt. But current is defined as dq dt, the rate at which the charge is changing. So we can write this a second order differential equation. We need a function for Q such that when we take the second derivative of it, we have the same function back but a negative sign. Well, we already know it's oscillating, so it's already going to be sine or cosine. With the way I set up the circuit, I said that the capacitor came in charged initially, and so that's why I drew the graph like that. If that's the case, then the charge is some cosine function. So Q naught cosine of omega t. Q naught being whatever initial charge or maximum charge the capacitor has. That means current's the derivative of the charge with respect to time. Derivative of the cosine function is negative sine. We have to take the derivative of the inside, which is omega. So we get the current being negative omega Q naught sine of omega t. Negative sine function starts at 0 and goes down. hard to make these line up. So the charge and the current are 90 degrees out of phase with each other. That means if charge is maximum, current is 0. If charge is 0, current has a maximum value. If charge is maximum, then the capacitor has all of the energy, so the inductor cannot have any of it. If the charge is 0, then the inductor needs to have all of the energy. Anywhere in between, we end up with both of them having some energy. What does this term represent? Whatever's in front of the sine or cosine function represents the maximum value of whatever the function is. So I max, the maximum current that flows in this circuit, is equal to omega times Q naught. Now omega, we need to figure out what omega is. If we come back to our equation here, Q over C plus L di dt, I'm going to put in Q here for Q over there. So Q naught cosine omega t over C. So that's the first term. The second term is L times the second derivative, so we need to take the derivative again. The derivative again, derivative sign is cosine, we're going to get negative omega squared Q naught cosine omega t. There's a Q naught in both terms, so if we divide by Q naught, they're going to cancel out. 0 over Q naught is still 0. There's a cosine omega t in both terms. So we have 1 over C minus L omega squared is equal to 0. So 1 over C is equal to L omega squared, or omega is the square root of 1 over LC, which is the same thing as 1 over the square root of LC. The units of omega are radians per second. It's an angular frequency, but it's still related to regular frequency in hertz. How do we go from radians per second to hertz? There is a pi in there. Omega over 2 pi is regular frequency in hertz. So this is the rate at which this system oscillates at. It has, we call it a natural or resonant frequency. It's the frequency it naturally wants to resonate at. In going back to the whole car stereo, for example, or your radio, if you want to change the radio station, you're changing the value of L or C so that you're changing this natural frequency. What's happening is all of these radio waves are coming in, and they're exciting the electrons in your antenna. But the electrons that are oscillating at the rate that matches this natural frequency are the ones that are oscillating the most. Remember the concept of resonance? Think about pushing a kid on a swing. You push a kid on a swing at the same rate they're swinging at, they go higher and higher and higher. The electrons that are oscillating in the circuit at this natural frequency will create the biggest current in your circuit, and that's the reception that you get in your radio tuners.
So, could Imax also be your amplitude?
Imax is the amplitude of the current. That's what it means. Amplitude just means maximum value, but it's the maximum value of whatever the function is describing. So saying this is amplitude, which would be perfectly valid, it still means it's the biggest current value that you can get because this equation is describing the current. So a 50 microfarad capacitor, we charged it to 12 volts and then connected it across a 60 millihenry inductor. What is the maximum current that will flow in the circuit? So capacitor, inductor, this makes it an LC circuit. We know I max is omega times Q naught. Omega we can find easily. 1 over the square root of LC. What about Q naught? Y'all staring at me like this is... I've never seen anything like this before. What units does charge have? Okay, so can Q naught be 12 volts? No. But we certainly can get Q naught from 12 volts. They're related. Exactly right. So Q naught so C 50 microfarads, delta V is 12 volts over the square root of L times C. When you make these calculations, you do need to put in 10 to the negative 6 for micro, 10 to the negative 3 for milli. They need to be in the farads and the henries. That's the solution to this question, yes. So the maximum current this circuit will see is 0.35 amps. It will never get bigger than that unless you somehow get more energy into the circuit. The current will oscillate between positive 0.35 amps and negative 0.35 amps. Oscillate back and forth. At some point in time, the current will be 0.2 amps. I would like to know how much charge is on the capacitor when the current is 0.2 amps. So when the current is 0.35 amps, the inductor has all of the energy. There's no charge. Q for the capacitor is 0 at that instant. If the current is less than the maximum value, then the inductor only has a portion of the energy, and the capacitor has the rest. So there's a couple ways we can do this. I don't know that one way is necessarily easier than the other. One way is to look at conservation of energy. We know that the total energy in the system at this instant in time is going to be shared between the capacitor and the inductor. We can easily find the total energy. The total energy came in with the capacitor. The capacitor is the one that came in with the energy. The total energy, on a capacitor, we can find 1/2 C delta V squared. We know capacitance, we know delta V. When the current is 0.2 amps, there will still be some charge on the capacitor. So the capacitor will still have some energy. Energy for a capacitor can also be written as 1/2 Q squared over C. I'll put a delta V naught on there, so remember it's the initial voltage. The inductor is also going to have some of the energy, 1/2 Li squared. We know I, we know L. Turns out the halves all cancel. C delta V naught squared, let's bring the L I squared over. That leaves us with Q squared over C, so if we bring the C over and square root it, that will be Q. And again, when you plug it into your calculator, you have to put 10 to the negative 6 in for micro and 10 to the negative 3 in for milli. So the charge on our capacitor is 4.9 times 10 to the negative 4 coulombs, or if you want, 490 microcoulombs. That's the amount of charge the capacitor has stored on its plates when the current is 0.2 amps. Another way to arrive at the same answer, I don't know that one's necessarily easier than the other. We can use our current equation. We now know omega Q naught, because that's the maximum current. We can figure out omega. We know the current is 0.2 amps. Solve for T, and then come back to the charge equation, and solve for charge. I don't know, I mean, it's a matter of opinion as to which way's easier than the other.
Still have to find Q of T, right? C delta V.
Q naught would be the C delta V. Because Q of T is what you're looking for. You're looking at for the charge at that time. Q naught would, yes, still be C delta V. Omega would be the 1 over the square root of LC. Use whatever time you got and solve for Q.